Good morning and welcome to video number 330. In this video, I am going to discuss part 2 of autoregressive models. In the previous video, I discussed introduction, stationarity, univariate, multivariate, and other details regarding AR model were discussed in the previous video. In this video, I am going to continue the same with the moving average and ARMA models and ARIMA model. So, as you know, moving average models should not be confused with the moving average smoothing. And the motivation is that we may recall that in auto-regression models, current behavior xt is regressed using the previous observation of xt, that is xt minus 1 up to xt minus p plus an error term w2 at current point in time. However, one of the problems with the AR model is that ignorance of correlated noise structures in the same series, which is unobservable. In other words, the imperfectly predictable terms in current time wt and previous steps wt minus 1, wt minus 2 up to wt minus q are also informative for predicting observations. The definition of moving average model is a moving average model of order q, that is MAQ, is defined to be xt is equal to wt plus theta 1 wt minus 1 plus theta 2 wt minus 2 up to theta q wt minus q, and that is equal to w2 plus summation j varies from 1 to q theta j wt minus j, where wt is white noise and normally distributed with the zero mean and variance theta square w, and theta 1, theta 2 up to theta q are parameters. Now, contrary to AR model, finite MA model is always stationary because the observation is just awaited moving average or past forecast errors. Moving average operator equivalent to autoregressive operator, we define moving average operator as theta b, and that is equal to 1 plus theta 1 b plus theta 2 b square plus up to theta q b raised to the power q, where b stands for backshift operator and thus bwt is equal to wt minus 1. This is the example of MA1 process, and here is a simulated MA1 process where xt is equal to wt plus 0.18 times wt minus 1. Mean of ext, expected value of xt is equal to 0 and variance is equal to sigma square w times 1 plus theta 1 square. This is the autocorrelation function of MA1 process, and this is the partial autocorrelation function of MA1 process, and this is the example of MA2 process. Again, the mean of expected value of xt is equal to 0 and the variance is given by this equation. This is general MAQ process, and an important property of MAQ models in general is that there are non-zero autocorrelations for the first q legs, and phi h is equal to 0 for all legs h is greater than q. In other words, the autocorrelation function provides a considerable amount of information about the order of dependence q for MAQ process. Identification of an MA model is often best done with the ACF rather than the PACF. Comparison between AR and MA. In fact, all causal AR of order P processes can be represented as a moving average with infinity, and in other words, infinite moving average process are finite autoregressive processes. All invertible MAQ processes can be represented as AR infinity, that is, finite moving average processes are infinite autoregressive processes. Parameter estimation, as we know, the fact that the parameter estimation of MA model is more difficult as compared to the AR model, and one reason is that the lagged error terms are not observable, but we can still use a method of moments estimators for MA process, but we won't get the optimal estimators with Yule-Walker equation. In fact, since MA process is nonlinear in the parameters, we need iterative nonlinear fitting instead of linear least squares. ARMA models. Autoregressive and moving average model can be combined together to form ARMA models. as the name shows, ARMA is the combination of autoregressive and moving average models. And the definition is a time series xt where t is equal to 0, plus minus 1, plus minus 2 and so on is ARMA of order p and q if it is stationary, and xt is equal to wt plus summation I varies from 1 to p phi I xt minus I plus sigma j varies from 1 to q theta j wt minus j. Stationarized non-stationary series. One limitation of ARMA model is the stationary condition. In many situations, time series can be thought of as being composed of two components, a non-stationary trend series and a zero mean stationary series, that is xt is equal to mu t plus yt. So what strategies can we use? We may detrend, that is detrending can be used, and in that we will subtract with an estimate for trend and deal with residuals. And another strategy is differencing. Recall that random walk with drift is capable of representing trend. Thus we can model trend as a stochastic component as well. Differencing. One advantage of differencing or detrending for trend removal is that no parameter estimation is required. In fact, differencing operation can be repeated. The first difference eliminates a linear trend. A second difference, the difference of the first difference can eliminate a quadratic trend. So we may recall the backshift operator, and we have like equations, the following equations. Here are three graphs. One is of original series, the second one is the detrended series, and the last one is the first difference. And this is the monthly totals of US airline passengers from 1949 to 1960. And you see there are some fluctuations, and there is overall trend in this time series. Now we can identify model for this. As with any data analysis, first of all we should construct a time plot of the data and inspect the graph for any anomalies. The most important thing is in this phase is to determine if the time series is stationary and if there is any significant seasonality that needs to be handled. So we may recall the definition of test stationarity. If the mean or variance changes over time, then the series is non-stationary. Thus an intuitive way is to plot rolling statistics. We can also make an autocorrelation plot, as non-stationary time series often show very slow decay. A well statistical test called augmented Dickey-Fuller test can be helpful, and the null hypothesis is that the time series is non-stationary. And this is the rolling statistics with sliding window of 12 months. So we have standard deviation and the rolling mean, and here we have the stationarity test, that is the ADF test, augmented Dickey-Fuller test. The test statistic is a negative number. The more the negative this number is, the stronger the rejection of the null hypothesis. Stationarize the time series, and these are various ways. All the previous methods show that the initial time series is non-stationary. It is necessary to perform transformations to make it stationary for ARMA modeling. So we may use detrending, differencing, transformation, aggregation, smoothing, and decomposition. And this is standardized time series autocorrelation function plot, and we have rolling mean and standard deviation function and the original series. And this is first order differencing over logarithms of passengers. And this is also again results of the augmented Dickey-Fuller test. From the ACF plot we can see that the mean and standard deviations have much smaller variation with time. Also the augmented Dickey-Fuller test statistic is less than the 10% critical value, which indicates that the time series is stationary with 90% confidence level. These are autocorrelation function and partial autocorrelation function, and we may choose model specification, and we may notice an obvious peak at h is equal to 12 because for simplicity we didn't model the cyclical effect. So it seems that P2 and Q2 is a reasonable choice. Let us see three models, that is AR2, MA2 and autoregressive moving average 2-2 model. So here is the AR2 predicted and residuals. Since residual sum of square is the measure of discrepancy between the data and the estimated model, the smaller the RSS it indicates a tight fit of the model to the data. This is MA2 process predicted on residuals. This is ARMA2 predicted on residuals, and here we can see that AR2 and MA2 models have almost the same RSS, but combined is significantly better. So here is the forecasting. The last step is to reverse the transformations we have done to get the prediction on the original scale. So these are the graphs. One problem in the ARIMA model is that there is lack of seasonality which can be addressed in generalized version of ARIMA, and that is known as seasonal ARIMA. And the definition is a seasonal ARIMA model is formed by including additional seasonal term in the ARIMA models denoted as ARIMA PDQ, where P is the order of autoregression, D is the order of differencing, and Q is the order of moving average. And in this model, M represents the number of observations per year. The seasonal part of the model consists of terms that are similar to the non-seasonal components but involve backshifts of the seasonal periods. Ladies and gentlemen, I thank you very much for your attention, and these two videos, that is video number 329 and 330, are a complete theoretical description and discussion of the ARMA, ARMA and ARIMA models. I hope these two videos may be helpful and informative regarding the ARMA and ARIMA models. If you haven't yet subscribed to this channel, kindly do subscribe to the channel, and do not forget to click on bell icon. Thank you very much for watching this video and the channel. See you.